In this lecture, we take a look at two more examples involving the work energy theorem. These are examples that were simple examples as dynamics situations that we looked at in the previous unit, but now we're just going to approach these problems by using the work energy theorem and get an idea of the energy transfers that occur. Okay, go ahead and copy the first of these two problems into your notes. Let me read it to you here. A box of mass 1 kilogram is initially at rest. A horizontal force of 20 newtons is applied and the coefficient of kinetic friction equals 0.3. Use the work energy theorem to calculate the speed of the box after it has been pulled for a distance of 3 meters. This is, of course, an easy dynamics situation, that is, by using F equals ma as your starting point and then using some kinematics to find the final speed. But we're going to approach this problem instead by using the work energy theorem. Okay, let's begin by drawing out the situation. Okay, so very simply, right here is our box like so. It's initially at rest. Okay, it has a mass m of 1 kilogram. And then I come along, for example, and exert a horizontal force in this direction. We'll call it F pull. That's given to us as 20 newtons. There's a coefficient of kinetic friction between the box and the surface below. That's given to us as 0.3. And then ultimately, I then pull the box like so over a displacement delta r. That's given to us as 3 meters. And then the box ends up over here like so at the end of the problem with a final speed v. Okay, now even though we're not going to use Newtonian mechanics to solve this problem, we're instead going to use the work energy theorem, you still go through the motions of drawing out a force diagram because you need to show the relationship between the force vectors and the displacement vector. So very simply, as we pull the box to the right-hand side, we have the following forces acting. First of all, we have the normal force and the force of gravity. They cancel each other out. We then have here horizontally F pull to the right-hand side. This is in the same direction as the displacement vector delta r, but of course opposing the motion is the force of kinetic friction. And now our starting point is the work energy theorem. We then write that down first. So net work equals change in kinetic energy. Okay, always begin by filling in the right-hand side of the expression first because it's always the same thing in the following sense. It's the final value of kinetic energy, 1/2 mv squared, minus the initial value of the kinetic energy, which in this case is equal to 0 because the object begins at rest. So you always write down the final value of 1/2 mv squared minus the initial value on the right-hand side of the expression first. And then the left-hand side of the expression are all of the individual work calculations, and then we add them together to get the net work done. Now, by this point, you could immediately start taking some shortcuts. For example, we already know from the previous example that I did in the previous lecture that the work done by the normal force is equal to 0 because there's a 90-degree angle here between n and delta r. Similarly, with gravity for this horizontal situation, there's a 90-degree angle between the gravitational force vector and the displacement delta r. So then therefore immediately the work done by those forces is equal to 0, and I'm not going to even bother writing them down at this point. But then of course we have the other forces. First of all, say F pull. So the work done by F pull is the dot product between F pull and the displacement vector delta r. And then we just use the definition of the dot product, of course, to make this calculation. So we have the magnitude of the first vector times the magnitude of the second vector, and then multiplied by the cosine of the angle between the two vectors. Notice that there's a 0-degree angle between F pull and delta r. Cosine of 0 is equal to positive 1. So then therefore, we essentially just end up here with force times distance. Like so. Okay, now this number right here, we now know what this number means in the context of work, that is, in terms of energy transfer. So the work done by this force is going to be a positive value. What that then means is that this force, F pull, transfers energy to the object. So for example, if I take something and I just pull it across my desk, I'm just going to use my clipboard here on my desk like so, and I do this with it, and I let go of it, and then therefore the clipboard has some final speed. Well, in part, some of the energy that I'm using here to do that work is being transferred to the object and becoming its kinetic energy. However, we also have kinetic friction between the object and the desk below. So there's going to be heat loss, We then calculate that by finding the work done by kinetic friction. So let's set up that dot product next. Okay, so the work done by kinetic friction is the dot product between the kinetic frictional force vector and the displacement vector. And then this value here is exactly the same as it was in the previous problem from the previous lecture. Ultimately, you end up with this term here once again. The negative sign comes from the cosine of 180 degrees. There's a 180 degree angle between F sub k and delta R. The force of kinetic friction is the coefficient multiplied by the normal force, which is equal to the object's weight. The negative sign means, once again, that this force, kinetic friction, removes energy from the object. Recall that that energy that's being removed is being transferred to the surface below. It's becoming another form of kinetic energy. It is becoming heat. Okay, so now I'm going to go ahead and add these two terms together, plug it in here to the left-hand side of the expression of the work energy theorem. Okay, so right here is the work done by F pull plus the work done by kinetic friction. This then equals the right-hand side of the expression, like so. And then in just a moment, I'm going to go ahead and just solve for the speed v. But before I do, the most important part of these problems that I'm doing as examples for the work energy theorem is to understand the energy transfer. What becomes what? In order to see the energy transfer, what we need to do is move the terms around a little bit and then show them as positive values. So here's what I mean by that. What I'm going to do is take this expression here for kinetic friction and move it to the right-hand side of the expression. It's not necessary for me to do this to solve for the speed v, but it is necessary to see the energy transfer. Okay, once again, the energy transfer is the most important part of the problem. So let me emphasize that here, like so. So let's move this term here to the right-hand side, and when I do, I get this expression here. And once again, think of this as what form of energy becomes what other forms of energy. Well, right here on the left-hand side, this is the energy that I use when I'm pulling the clipboard across my desk. So this right here is the energy used by the external agent, as we say. The external agent being me. And then what happens to the energy that I use? Well, it becomes two things. It becomes, for example, right here, the kinetic energy of the object and also the heat that is transferred to the surface below. Okay, I'm kind of running out of room here to write this. So let me do this. So this right here is the kinetic energy of the object. And then this right here is the heat transfer. This is once again the heat transfer to the surface below. Okay, and then let's just go ahead and finish the problem. Let's jump back to here and solve for the speed v. Be a little bit careful. The mass does not cancel from the expression because the mass is not present here in this term. So let's go ahead and multiply this quantity here on the left-hand side by 2, divide by the mass m, and then take the square root. So after you do those mathematical steps, here's the expression that you end up with. Like so, and now we just plug in. Now, technically, of course, when you're taking a square root here, there's a plus or a minus. What do we do about the minus sign? We ignore it. The reason for that is because this is not a velocity that we're solving for here, it's a speed. Remember that ultimately, all of this comes from dot products, which gives you magnitudes of vectors. So then therefore, this is not a velocity that we're solving for, it's instead a speed, so we just keep the positive value. Okay, let me go ahead and plug in everything. I'm going to do the parentheses here first. Let's see, what was F pull? That was 20 newtons, multiplied by the displacement of 3 meters, and then minus the coefficient, times the mass, times g, times 3 meters. Okay, take all of that, multiply by 2 divided by 1, and then finally, after all of that, take the square root of that. And this comes out to be equal to about 10.1 meters per second. Once again, we could have solved this problem by using F equals ma, and then ultimately using some kinematics to find the speed v. But of course, if we did the problem in that manner, it would have said nothing at all about the energy transfers that occur. Okay, let's go ahead now and take a look at the second problem for this video. Let me go ahead and manipulate my file. I have to do some erasing on the board as well. Okay, so let me do some erasing. And the second problem here is going to involve the basic incline, which we've seen before with kinetic friction. As we set up and solve this problem in just a few moments, we're going to once again see that there is something special about the force of gravity, and you're also going to begin to see hints of another form of energy that is present. Okay, let me manipulate my file. Okay, so a mass is initially at rest on a 2 meter long, 30-degree incline with a coefficient of kinetic friction of 0.1. Calculate the speed of the mass at the bottom of the incline. Let me quickly demonstrate it to you here. Okay, so I've got my inclined surface like so, and then here's my object of mass m. We initially set it at rest here at the top of the incline. It then slides down to the bottom. We're asked to calculate the speed v. Okay, so setting up the problem. Here's our incline, like so. Here's the angle of inclination given to us as 30 degrees. We have a coefficient of kinetic friction present that's equal to 0.1. And then here's our object of mass m initially at rest here at the top of the incline. Okay, it then slides down to the bottom of the incline like so. It reaches the bottom with a speed v that's unknown, and then undergoes a displacement here on the diagram like so. This displacement that is given to us, delta r, is equal to 2 meters. Okay, now that displacement is the hypotenuse of this right triangle. What we're going to see present in this problem is a height change. That height change from here to here vertically, I'm going to refer to this as h. The height change is equal to the hypotenuse multiplied by the sine of the angle. It's 2 meters times the sine of 30 degrees, which is 1/2. This is a height change of 1 meter. So I'm including this here in our setup because we're going to see this appear later on in the problem as we proceed. Okay, now let's go ahead and set up our force diagram and then apply the work energy theorem. So as the object slides down the incline, the normal force is perpendicular to the incline. We of course have the force of gravity straight downwards like so. And then opposing the motion, right here is the displacement vector delta r down the incline. Opposing the motion like so is the force of kinetic friction. Even though we are not using F equals ma to solve this problem, I'm still going to take mg and break it up into its components. All right, so recall how that is done. What we do is we come down from the normal force like so, and then go across, and then right here gets formed on the diagram, the angle theta. Okay, now let's go ahead and set up our work energy theorem. Okay, so net work equals change in kinetic energy. And then you always begin by writing out the right-hand side of the expression first. So we're going to have a final kinetic energy of 1/2 mv squared, and then minus the initial kinetic energy of 0 because the object begins at rest. So, okay, and then we have the net work done on the left-hand side of the expression. We do our individual work calculations. Take a look at, first of all, the work done by the normal force. There is a 90-degree angle between the normal force and the displacement delta r. Cosine of 90 degrees from the dot product is equal to 0, so then therefore no work is done by the normal force. The incline itself lacks the ability to transfer energy to the object or remove energy from the object. This is the technical reason why the normal force vector has to be perpendicular to the incline. Now, I described this in our previous unit on dynamics. Here's how it's explicitly showing up in this basic example. The only way in which the normal force can do work in this situation is if an external agent, such as myself, is present. And then ultimately, if I say take the incline and do something like this, remember this rather facetious demonstration that I did in a previous lecture like so, only then can the normal force do work, that is, if I am present. If I am not present, if there is no external agent present, then the normal force must be perpendicular to the incline because the incline itself does not contain energy. It lacks the ability to transfer energy to the object or remove energy from the object. This is ultimately why, once again, the normal force must be perpendicular to the incline. Okay, but now let's go ahead and take a look at the other forces. Before I get to gravity, let's take a look at, first of all, kinetic friction. So the work done by kinetic friction is the dot product between kinetic friction and the displacement vector. Let's go ahead and set this up from scratch. So we take the magnitude of the first vector times the magnitude of the second vector multiplied by the cosine of the angle between the two vectors. As is always the case, there's a 180-degree angle between f sub k and delta r. Cosine of 180 is equal to -1. So we pick up our negative sign. Okay, and then the force of kinetic friction is the coefficient multiplied by the normal force, like so. And then the normal force is not equal to the object's weight mg in this problem. Instead, the normal force, remember, cancels out with this component right here of mg. This adjacent component here of mg on this right triangle is mg cosine theta. That then gets plugged into here. Let's go ahead and write this down. Like so. Okay, now if I take that expression for the normal force, I then plug it into here. And then right here is my expression for the work done by kinetic friction. Once again, this is a representation of the heat that is transferred to the surface below. And now we get to gravity. Okay, so the work done by gravity. In my previous problems that I've done in horizontal situations, the work done by gravity is equal to 0. Not so in this case when a height change is present. So let's go ahead and set up this dot product. So I have the dot product between the gravitational force vector and the displacement vector. So we take the magnitude of the first vector times the magnitude of the second vector and then multiply by the cosine of the angle between the two vectors. Take a look at the diagram above. The angle that we need is the angle between mg and delta r. It's not labeled on the diagram, but notice that it's the complement of the angle theta. That is, that angle is 90 minus theta, like so. And now I'm not going to plug in the numbers here just yet. Once again, I want to carry this out a couple of extra steps to begin to see why the height change h is important. In order to do so, I'm going to employ right here a trigonometric identity. Specifically, I'm going to use the subtraction identity for cosine, which looks like this. Okay, I'll put it in brackets. We take the cosine of the first angle times the cosine of the second angle. Then there's a sign switch. It's plus the sine of the first angle times the sine of the second, like so. And then let's go ahead and simplify the brackets. When I simplify the brackets, cosine of 90 degrees is equal to 0. Sine of 90 degrees is equal to 1. So if you then clean up the expression that is left over, here's then what we obtain. Like so. And then right here, if you take a look at the top board, is the height change h. Like so. So we've seen this before. We saw this in a practice work calculation earlier in this unit. The work done by gravity depends upon the height change h. So now let's go ahead and add the work done by gravity, plus right here, the work done by kinetic friction. That then goes here in the left-hand side of the work energy theorem. Let me go ahead and write that here. Like so. And then in just a few moments, we'll go ahead and solve for the speed v. Before I do, however, once again, what's most important about these basic examples is to see the energy transfers that occur. And in this case, you're going to begin to see hints of a new form of energy that is present. So on the lower board, let me do some erasing here. And now let's see specifically the energy transfer that occurs. So the energy transfer now can be seen in the following manner. Take this expression for the work done by friction and move it to the right-hand side of the equation. When you do, you end up with this. Like so. Once again, always think of the energy transfer as what becomes what. What forms of energy become what other forms of energy. Now on the right-hand side of the expression, we already know what the terms refer to. This right here, for example, is the object's kinetic energy at the bottom of the slope. We already know what this is. This right here is the heat that is transferred to the surface below. The question is, however, what is this? Something that has to do with gravity and height is ultimately turning into kinetic energy and heat. Take a look at the physical situation. Something that has to do with gravity and the height change h. That's ultimately then transforming into kinetic energy and heat as the object slides down the hill. What do you suppose this just might be? If you're thinking to yourself potential energy, you are in fact correct. However, as you'll discover as we proceed through the remainder of this unit, exactly quantifying what is meant by potential energy and proving its existence is not trivial. So then therefore what I'm doing in this example is I'm introducing you to the idea of potential energy, but a little bit deeper into the unit we'll go through it more specifically. But for now, this right here, still have the question mark there, is a new form of energy that's present here in this situation, and that is called gravitational potential energy. However, let's go ahead and just solve the problem now at this point. In order to solve the problem, let's back up to this step here, and then I'm just going to solve for the speed v. So let me do some erasing. Like so. Okay, let's go ahead and get rid of that term. And now in this expression here, we can go ahead and cancel out the mass m, like so. And then I'm going to cross multiply the 2 over here to the left-hand side, and then take the square root. We'll then take the positive value to get the speed v. That then gives us the following expression. Okay, so cross multiply the 2 over, like so. Take the square root, and that then gives us the speed v, and at this point we just plug in everything. All right, so I'm going to do the parentheses here first. So I have 9.8 times 1, so 9.8, and then minus the coefficient of 0.1 times 9.8 times the cosine of 30 degrees, and then multiply that by 2 meters, like so. Multiply the whole thing by 2, and then lastly, take the square root, like so. And we end up with a speed of about 4.03 or so meters per second at the bottom of the incline. Okay, so with these two examples and the example that I did in the previous lecture, what we have seen here are some simple quantitative examples involving the work energy theorem.